Hi there, Math Angel. Welcome back. And a warm welcome if you are new around here. This is Decaf-Math, ASMR. I hope that this finds you well, and I thought we could just relax together in this moment, and celebrate this moment with a little bit of math. And today we're going to talk about how to classify triangles in two different ways. One way is based on the length of the sides, and the other way is based on the measures of the interior, the inside angles. This was a requested topic, but as always, it doesn't matter whether or not you're learning this, or even if you like math or don't, if you have fond memories of it or not, and whether or not you're even learning it or ever really cared. I'm just happy that you're here and right now. And I was just taking the time to appreciate that if you are watching this, that we both have access to the internet even. And if you're able to grab a mug of something warm and decaf, that we have access to water. And that's a blessing in and of itself. And so I'm so grateful to have this moment to slow down, and be together. So anyway, triangles. If you're looking for a quick tutorial, you've probably gathered that you won't find it here today. We're going to be going over the vocab words, and this is usually mentioned in geometry, but you might find that you've been playing around with triangles all your life and maybe never really knew that they had a name. So let's classify a triangle by length first, the lengths of the sides. Lengths of the sides. So first of all, a triangle is going to have 3 sides and 3 angles and triangle. So how about one like so? So what is this tool called? A straight edge, yes indeed, or a ruler. In this case I have lengths, or an indication of length, inches and centimeters. So it's a ruler, but when I draw a triangle, I'm just using the straight edge part of it to draw the 3 sides, and will also indicate that there are 3 interior angles, triangle, 3 angles. 1, 2, 3. And so the lengths can be measured, and so can the angles. We measure the lengths with the ruler, and we can measure the interior angles with a protractor. So the protractor is kind of like a curved ruler, 0, 90, 180, or going the other way depending on which way you're measuring, 0, 90, 180. We can go into more depth with this another time. But in theory, you can measure those angles. So first, if we classify by length, we can, let's say this is approximately 11 centimeters. This is approximately 14 centimeters. And this is approximately 7.5 centimeters. So we can measure like that. And in this case, we see that all three sides have different lengths. All of them are different. So we call that a scalene triangle. S-C-A-L-E-N-E. Scalene. A scalene triangle is a triangle where all the lengths of all the sides are different. All three sides are different. So remember, our triangle is going to be enclosed like this. So it's not just one length, two lengths, three lengths. It has to form this kind of cycle thing here, right? We have three vertices, these points, and so we're just going to be connecting the dots. So we will have three clear sides that are going to have lengths, and if they are all different, it's a scalene triangle. All different. So sometimes in a diagram, the lengths are written for you. Sometimes we have to measure. Other times, as you continue on in a geometry class or a trigonometry class, sometimes we're given some information but not another, but we can learn and use some rules to help us figure out what certain lengths or angles are. And that's a lot of fun too. It's like a little puzzle. But either way, sometimes it's indicated in a diagram, or other times you can just use your ruler and measure to decide for yourself, okay? Alright, so all of them are different, makes it scalene. If we have two that are the same, and technically at least two, but we'll get into that. If we have two lengths, let's say, like so. 1, 2, 3. And these are both 7 centimeters. Then we call this an isosceles triangle. Isosceles. 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 And you can take your time in understanding the spelling of this. I'm going to have to double check it after this video. Isosceles. Man, thank goodness we are not in a spelling bee right now. It's not isosceles. Isosceles. That's where we have two sides with the same length, and I say at least two because technically the third could also be, in this case, 7 centimeters. But if we have two, and even if this were not, so this could be, in this case it's not 7, we have about 6.5. It's still isosceles. We have two of the same length of side. Okay, that's isosceles. And you've probably guessed it. We either have all of them different, or two of them the same, or three of them. So if they are all the same, we have an equilateral triangle. Equilateral. Equilateral. Equilateral sides. Equilateral. So, I think you get the idea. I can shift this 6 or this 7 out a little bit and make them all 7. 7, 7, 7, and that would be equilateral. Okay, so now we have 3 ways to classify pi lengths, and let me highlight them one more time for us. Scalene is all different. Isosceles is when we have at least 2 of the 3 being the same length. And equilateral is when they are all the same. So now there's a very interesting question that might come up, which is an equilateral triangle also isosceles? Is an equilateral triangle where I have all 3 sides the same isosceles? My answer to that would be yes, because if 3 of them are the same, 7, 7, 7, then we have at least 2 of the 3 lengths the same. It just happens that the third one is also the same. When we talk about properties of these, and when we learn more rules in geometry and trigonometry, the rules for this apply for these. So I like to classify that in this way. I think that every now and again, but very rarely, will you see that an isosceles triangle is defined as having exactly 2 of the same and the third one being different. different, but you might. And so I wanted to include that idea. Okay, so that would make it so that an equilateral would not be isosceles because all three are the same for equilateral. But this is how I've learned it, this is how I prefer it, and this is how I've most commonly seen it. But it's not unheard of, okay? And kind of an equivalent idea is rectangles and squares. So a square is a certain type of rectangle where the four sides have the same length, but it's still classified as a rectangle. So it's the same thing in my mind for equilateral also being isosceles, but it just happens to have all three with the same length rather than exactly two. Okay, so we have classifications by lengths of sides. And now, as you've probably guessed, we are going to be classifying by the interior angles. So, this is just a matter of how wide or narrow or whatever, right, our triangles are. If we have a triangle with angles that are all less than 90 degrees, it's cute. It's called an acute, but I think it's also cute. An acute triangle. So that's our first word. It's cute with an A. A-C-U-T-E. And we can actually classify angles in general, just a single angle, as being acute, or all these other words. But with the triangle, with acute, all acute angles, all angles that are less than 90, that would be an acute triangle. Okay, so I'm gonna sketch it like that. This is less than 90 degrees, 90 degrees being a right angle like this. 90 degrees. So if it's all less than 90, again, you can use your protractor to measure if needed. Okay. In this case, it would be about 60 or so. This is about 65, right? So these are all less than 90. These are all less than 90. That's an acute triangle. If we have a right angle, then it's a right triangle. So if I took this here and connected these two parts, this is a right triangle. A right triangle. And in this particular case, it's a little side fact here, but a very important one. The sum of the measures of all of the interior, the inside angles here, of any triangle adds to 180 degrees. 180 degrees. So, in this this particular case, I know that based on this kind of definition here, that the right triangle, for instance, can only have a 90-degree angle. I can't have two 90-degree angles, because if this were 90 and this were 90, then 90 plus 90 is 180, and that angle would have to be 0, which makes no sense. We would just have a line, and that's not a triangle anymore. So we have exactly one, and it kind of pigeonholes the other two to not be right. And not only that, it can't be more than 90 either, because the sum has to be exactly equal to 180, okay? So that's why I can also conclude that for acute, if they are all less than 90, then it's going to be acute. If I have an angle that is more than 90, it's called an obtuse. Obtuse. Let's see if I can squeeze one here. How about like so? Oops, still got cut off. Obtuse is going to look about like so. So this angle here is more than 90. It is wider. So we have little acute angles, then we have a right angle, and then we have wide obtuse angle. But since this is more than 90, and the interior angles have to add to be exactly 180, that forces the other two to be less than 90. So we're only going to have has an obtuse angle. So has an angle that is more than 90. So it literally has an obtuse angle. So okay, you see that? So an obtuse triangle has an angle that is more than 90, but just one. I think the easiest way to classify in this case is if you have a right angle, it's a right triangle. If you have an angle anywhere in it that is more than 90 degrees, it is an obtuse triangle. And then if you notice that they all happen to have angles, or all the angles are less than 90, then you have an acute. So I would try in that order, because if you just took a random angle and saw that it was less than 90, then you can't assume anything or conclude anything for acute, because you would have to check that all three are less than 90. But if you automatically see an angle that is more than 180 or more than 90, then you have an obtuse. And if you automatically see one that is 90, then you have a right without having to check the other two. Okay, so that's my suggestion for that. But if you've learned about angles, then these words might kind of look familiar to you anyway. A right angle, an obtuse angle, acute angles, and so we can also generalize that for triangles. And that's about it. As far as angles go, strictly speaking, an angle is going to be two rays. So this should continue on to infinity, and this would continue on to infinity, and they intersect. But because we're doing this for triangles, we kind of cut off this ray here to make this other ray here. So it's kind of the intersection of 3 angles. So technically for this angle, it continues on here and continues on here to infinity, but we're intersecting them all. So they're kind of angles. We can still measure the angles, but it's really the intersection of these to form our proper triangle. Okay, as far as that goes, I think from there on in geometry, we like to do some fun and cool rules like lengths of sides opposite of angles and stuff like that. That's a bit of trigonometry work as well. Triangles and more deeper triangle work. But I hope that this was helpful. If you're asleep now, I wish you sweet mathy dreams. And if you're continuing on with the rest of your day, I wish you a nice rest of your day. Thanks for joining me, and